intersections. I'm really happy about this because I think people might be a little bit tired of it just being mostly me and Jerry all the time. As much as I enjoy doing them, I think having a fresh voice is great. So I'm really looking forward to this. So, Sharon, take it away.
All right. Is it on now? Yep. Awesome. All right. So my topic tonight is the composition of the universe, and specifically I'm going to be talking about the atomic universe. So that's kind of the abundance of certain elements. So when I first started planning this talk, people would come up to me and ask, what's your topic going to be? And I would tell them. And I've kind of left the conversation feeling a bit disappointed because in actual fact, the universe is a lot of hydrogen, just like a lot of hydrogen, which will make for a very short talk, I think. So there is also some helium and other elements, but those elements make up like barely 1%. But I did continue looking into it because I was kind of committed at this point, and I actually found some pretty interesting stuff. We'll start with the basics. Since November 2016, the periodic table, as you all recognize, contains 118 known elements. 94 of those can be found naturally occurring on Earth, and 24 of them are synthetic, so we kind of have discovered them through lab experiments. Everything that we eat, touch, smell, breathe, wear, and physically are can be found in some form on the periodic table. Hydrogen and helium are the most abundant by far. Most of the hydrogen and helium that we find in the universe is actually primordial, meaning that it comes from the Big Bang. But the question is, where does the rest of it come from? So now I'm going to talk about the structure of an element, which is important. Each atom of an element has a nucleus, made up of protons and neutrons. So that's right there, with outer shells of electrons that kind of move about freely. As you get higher in the periodic table, the more neutrons and protons you have in their nucleus. And that's kind of how we identify an atom, based on how many protons are in its nucleus. Typically a neutral atom would have 1 electron for every proton. If you take that away though, then it becomes ionized. So we have a certain way of indicating these. H1 stands for neutral hydrogen. H2 means that it's ionized, so it's lost its electron. Hydrogen only has really 1 electron to begin with, so it can only lose 1. But oxygen, which has 8, can lose more. So O3 stands for oxygen that has lost 2 of its electrons. This is important because it actually happens quite a lot in the universe. It's frozen. There we go. So let's start in our own backyard. Earth has a volume of over 1 trillion cubic kilometers and the mass of 5.9 septillion, or 5 trillion kilograms. If you divide the mass by the volume, you get an average density of 5.5 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter, and the Earth's crust, which we're standing, or in most cases sitting on right now, has a density of between 2 and 4 grams per cubic centimeter. So why does the Earth seem to weigh so much? We figure that the core of the Earth must be metal, probably iron, and it's split into 2 parts. It's got the solid part and then an outer core, which is actually liquid, and it's still made of the same stuff. So it's iron probably mixed with sulfur and nickel. Because of the gravitational pressure of all the layers piled on top, it makes the core actually really, really dense, so which explains why it's so heavy. Between the core and the mantle, or between the core and the crust is the mantle. It's pretty much rock made of a jumble of elements, mostly oxygen, magnesium, silicon, iron, and aluminum. So that's that area or that area, depending on which piece of the Earth you care about. The crust is also rocky, consisting of igneous rock, so it was formed from lava. It's also known as basalt, which is similar in makeup to the mantle, and it has the same elements, just different distribution. Above the solid and liquid surface of Earth is the atmosphere, which is made up of 78% nitrogen, less than 21% oxygen, and less than 1% argon. Everything else, including carbon dioxide, neon, helium, methane, and water vapor, makes up trace elements, but that doesn't mean that it's any less important, as we've observed in the past few years. The atmosphere becomes less and less dense as it gets further away from the Earth's surface. I found it interesting that the Earth did not always have such well-defined layers. In fact, in its early years, all these materials were kind of distributed like a really bad fruitcake. And it was evenly distributed, but then the interior heated up and everything became molten to the point where denser materials like iron could fall to the very middle and lighter materials could float, I guess, to the top or the outer part of the Earth. When the Earth cooled down again, they kind of froze where they are, and that's how we get the distinct layers that we find here. But overall, you'll find all the naturally occurring elements at different levels of abundance in the Earth. So Earth gives us a real variety, which is nice because all our experiments kind of start here, so we have a great base for learning about the rest of the universe. The other objects in our solar system give us another perspective. We're going to start with the ones that really imitate Earth in some way, or well, maybe Earth imitates them, who knows. But some objects immediately remind us of Earth, like the Moon and the terrestrial planets, so that would be Mercury, Venus, and Mars, respectively. You can't see, can you see the labels? Can everybody see the labels? Okay, well, Moon, obviously, Mercury, Venus, Mars. While they vary in size, the Moon, Mercury, Venus, and Mars shares many characteristics reminiscent of Earth, like a solid, iron, or metallic core, surrounded by rocky mantles and rocky crusts with their own volcanoes and craters, in most cases. But there are slight differences. For example, the Moon, it has calcium, aluminum, titanium, uranium, and thorium in its mantle and crust, so a little bit different than what we're used to. The Mercury has a core that takes up 80% of its radius, and Venus has an atmosphere of carbon dioxide with clouds of sulfuric acid, so don't usually find those on Earth. Mars is so Earth-like with its water ice that we want to entertain the idea that it either has hosted life forms or it will host life forms in the future. So we're kind of familiar with these compositions, even if they are still considered alien landscapes. Places that were not so familiar to us are the Jovian planets, affectionately known as the giant planets. So they lie further out over there. They're quite large, hence the name giants. Jupiter and Saturn are gas giants, whereas Uranus and Neptune are classified as ice giants. Jupiter is the closest and the biggest by far, although Saturn definitely is no small fry. They're mostly hydrogen and helium gas, although as you get closer, the extreme pressures of all the layers compress everything together, so that Jupiter and Saturn actually have the largest oceans in the solar system of hydrogen. We think they may have dense cores of rock and ice, but we're not entirely sure. Jupiter's atmosphere is ammonium and ammonium hydrosulfide. Plumes of sulfur and phosphorus pushed along by the jet streams create the distinctive kind of striped appearance of Jupiter. And Saturn itself is so light that if the universe were one giant bathtub, it would probably float. They each have a confirmed 53 moons, so 53 for Jupiter and another 53 for Saturn. All their moons are very unique, and there's over 100 of them, so I'm not going to really go into detail tonight, just know that there's a lot, and they're definitely worth exploring. Jupiter and Saturn each have rings. Saturn's are a bit more impressive, obviously, and those are probably made, or well, they are made of ice and rock, probably formed from dust from flyby moons or asteroids or comets. The ice giants are Uranus and Neptune, and they have the distinct kind of blue color, although it doesn't really show up very nicely there. Their distinct blue colors is caused by methane gas in their atmosphere. Neptune is a bit bluer, and we don't really know why that is. So we think there might be some kind of unknown component in its atmosphere. They're each 80% fluid icy matter, water, methane, and ammonia, with small rocky cores. Many of their moons are ice and rock. Now for the backup dances of the solar system. So there are dwarf planets included. You kind of see them over there, very nicely small labeled. And they're made of mostly icy material. There are also asteroids, and those are kind of rocky crumbs from our early solar system. We find most of them between Mars and Jupiter in the asteroid belt. They range in size from 500 kilometers across to 10 meters across. The most common type consists of clay and silicate rocks, although some do have nickel and iron. 9.8% of the meteors that we find in our atmosphere come from asteroids, while the rest come from the Mars and Moon. Comets are known as dirty snowballs because they're made of icy matter coated in organic matter. This is important because these are critical materials for the development of life, so we think that comets probably have a significant role in the development of life on Earth. Comets also make up the Kuiper Belt, a ring of icy bodies kind of spread like a disk past the orbit of Neptune. We only see them when one strays close enough to the sun that its ice turns to gas and it forms some tails. It forms two tails. One is dust and the other is ions. In between all of this is the Interplanetary Medium, which is what we would consider empty space. Well, it's not empty, it's just very sparse. Sparse enough that we can't emulate it with any vacuum on Earth. The interplanetary medium contains microscopic particles of dust, as well as gas and plasma. So plasma is a type of gas made up of ionized elements, along with electrons, and all together a big plasma cloud is overall neutral. But all of this comes from our sun, which expels these materials into the interplanetary medium at incredible speeds in the form of its solar wind. Amazingly, if you measured every planet, satellite, asteroid, comet in our solar system, it only makes up 0.2% of the mass of our solar system. Even Jupiter, which is twice the mass, even Jupiter, which contains more than twice the mass of all the other planets combined, doesn't even make a dent. Now, before we move on, I need to explain some scientific stuff called spectroscopy. Using spectroscopy, scientists can determine the chemical composition of astronomical objects. And what they do is they analyze the light spectrum. So that would be this. But it's more kind of what you would see through a prism, except that it covers more than just the visible spectrum, there. Light seems to follow certain rules, which we know as Kirchhoff's laws. The first one is that if you have a hot source, whether it's liquid, gas, or most likely solid, it will emit a continuous spectrum like this. The second is if you have hot enough gas, or just a gas, it will emit only a little part of the spectrum, and that's called an emission line. If you have a light source shining through a gas cloud, then you end up with the gas cloud absorbing that light source, and it absorbs the part of the spectrum that it would normally emit, and you end up with the difference, which is an absorption line. So every atom and element in the table has its own kind of line signature, right? And scientists have kind of compiled their own catalogs of all of the light sources or emissions that different elements and even ions like the H2 and the O3 give off. So when we look at an object, we can almost certainly know kind of what it's made of. The brighter the object, of course, or the brighter the emission line, the more abundant we figure the element is. So the closest and most obvious example for us to use this on is our sun. Considering it makes up over 99.8% of the solar system's mass, it's probably a good idea to know what it's made of. Spectroscopy comes in handy when measuring the composition of the sun, for sure, since we can't exactly get samples of it. The sun has a diameter of about 1.4 million kilometers, a mass of 2 million kilograms, or 2 billion trillion kilograms. Still, it only has a density of about 1.4 grams per cubic centimeter, and if you'll remember, water, or the Earth rather, has a density of 5.5. So we are pretty sure that the sun is just a giant ball of gas. Mostly what we see is the sun's atmosphere, which includes the photosphere, the chromosphere, and then the corona. The visible part of the sun is the photosphere. So at this layer, the energy generated in the sun's core escapes and produces light, which makes it the most easily observed part of the sun. Even though it's gas, it is still opaque, so it's impossible at this point to see into the sun's interior. So we try to use the photosphere as a reference for the rest of the sun. The next layer up is the chromosphere, which is usually outshone by the photosphere, except in the case of a total solar eclipse, when it shows up as this kind of vivid red color. That's because of the hydrogen, and the hydrogen kind of gives off light in the red part of the spectrum. The uppermost layer of the sun's atmosphere is the corona, which looks like a nice white halo, and also can't be seen except during total solar eclipse. And this is actually just streamers of plasma bursting outward into the interplanetary medium. As for the core, the temperature is about 15 million Kelvin, which is hot enough to literally fuse atoms together in a process called thermonuclear fusion. Our sun fuses hydrogen nuclei to make helium, and this process in the core actually produces energy, and that's the energy that you see escaping in the photosphere. Here are two pie charts that kind of break down the elemental abundances of the sun. One is by the number of atoms, it's a totality of the number of atoms, and the other is by mass. The reason they're different is because hydrogen, having the least number of protons and electrons and neutrons, is the lightest element, and then helium, and then so on and so forth. So you see that if you counted them, you'd have more hydrogen, but if you weighed them, you would have not quite as much hydrogen, but still a lot of hydrogen. So yeah, it still seems kind of boring at this point. But then you have to take into account that our sun is relatively small, and while we're quite proud of it, it's not really much special. In fact, it's kind of mediocre. Sorry if I hit anyone there. There are many different types of stars. They range in temperature, color, size, obviously, as you can see, and type. That would be O, B, A, F, G, K, M. And this words from the solar diagram. A really cool diagram to look at if you have time. Our sun is neither the smallest, nor is it even close to the biggest that we've ever seen. But stars, similar to our sun in mass, never get hot enough to fuse helium into heavier elements. So they just kind of run out of energy, and they blow up into giant or red giants before collapsing into carbon-white dwarfs. But stars with heavier masses have a different future. Once enough hydrogen is fused into helium, the core will contract, it will increase the temperature, and that will allow helium to fuse into carbon nuclei. So you end up with a core of carbon surrounded by a helium-burning shell, which itself is surrounded by a hydrogen-burning shell, which also has a photosphere and a chromosphere, or chronol itself. If a star is massive enough, it will continue to fuse different elements into others, like oxygen, neon, magnesium, silicon, and finally iron. Iron is where it stops, because iron is the most stable element. It's so compact that it would actually take energy. It would take energy instead of give off energy in the process of fusion. So an evolved an evolved star ends up with all these layers of increasingly heavier elements. And its central temperature rises. The burning rate accelerates, making it very unstable. At this point, iron can't give off any energy, like we explained, which disrupts the equilibrium of the star. There's no pressure from the energy pushing outward, so the gravity of the star overwhelms it and it implodes very impressively. The collapse, The collapse accelerates until the core overshoots its point of equilibrium, reaching densities as high as a quadrillion grams per cubic centimeter. So heavy. This is a bit much, so the star kind of bounces back, creating an explosion. This explosion is so bright that we have observed it happening in other galaxies millions of light years away. And all of this kind of happens in the space of a second. As you can imagine, this causes an enormous shock, which just blasts all the elements that the sun has been working very hard to make into the interstellar medium. We call this a supernova. This is a photo of the Crab Nebula, which is actually a supernova remnant from a supernova that was observed from Earth in the year 1054. This is what it looks like today in false colors. Different colors kind of signify different elements or ions. It's about 6 to 10 light years across. I've got varying numbers on that, but it's very big and it's still growing. The material from this supernova will be recycled to form more stars. It should be noted, however, that this is all very simplistic. Not all stars will develop iron cores, nor will they all blow up into supernova. If they do, they might have different elemental abundances, or they might have been caused by different things. But the main drawback, or the main take forward from this, is that from simple hydrogen and helium atoms, you can actually form very heavy elements, which, remember, is important for life to exist. So it ends up being pretty worth it, I think. All of this is occurring within an environment known as the Interstellar Medium, which is literally just the space between stars. Interstellar space is even less dense than interplanetary space. Are you asking a question, Kevin? No. Is even less dense than interplanetary space, with an average density of 1 atom per cubic centimeter. For comparison, the average density of air molecules at sea level on Earth is 25 million trillion molecules per cubic centimeter. The interstellar medium can be broken down into 2 main components, gas and dust. Gas is made up of individual atoms or molecules. Dust is more larger clusters of atoms. And by larger, I mean 1,000 times larger, but still microscopic, so don't try looking for it, except it actually shows up pretty well. The gas is so thin between stars that in an area the size of the Earth, you'd have barely enough matter to make a pair of dice. Dust is even rarer than gas, with an average of only 1 particle per million cubic meters. And yes, it's mostly hydrogen. All this matter is not spread evenly throughout the interstellar medium, but is actually kind of clumped together into clouds, and there are different types of clouds. One type is an emission nebula. Spectroscopic analysis shows emission lines, which, if you'll remember, means these nebula are gas. The Orion Nebula, seen here, is an emission nebula, which is made up of hydrogen right there, oxygen, and a little bit of helium. Bright nebula do not produce their own heat, but they actually kind of get the heat from really hot stars that are nearby them, and this helps ionize the atoms and makes them emit light. Often these nebulas are seen red in color, even looking at them without a filter. This is because the hydrogen line is so specifically red, and we call this the H-alpha line, and it outshines any other elements that are emitting in the nebula, usually. Because the abundance of ionized hydrogen in these nebula is so overwhelming, emission nebula are also known as H2 regions. Sometimes in these nebula, you'll see dark lanes, and those are actually dark dust clouds, which is another type of interstellar medium. Dust clouds still contain 1 trillion gas atoms per particle of dust, but because the concentration of dust in these clouds is so much more than otherwise or elsewhere in the interstellar medium, we still call them dust clouds. The thing with gas, as we learned from spectroscopy, is that it does not block out light. That is not quite the case with dust. Even though it only adds up to 1% of the total mass of interstellar matter, and it's spread so thin, there's still enough dust to obscure light from other objects. In fact, the best way to observe dust clouds, in my opinion, is to not see anything else, such as in the case of the Milky Way galaxy, or the Horsehead Nebula, or they're sometimes just with a background of consistent stars. These clouds are often fairly large, even larger than our entire solar system, and to see past the dust, we usually have to use radio or infrared astronomy. Alternatively, sometimes bright nebula aren't emission nebula at all, but actually dust clouds that kind of get reflected, or they reflect the light from stars inside. And these typically turn out blue in color. And that's what these, in case you didn't know, probably do. In some cases, if the dust particles or grains have a temperature of around 100 Kelvin, we find peaks in the infrared area of the electromagnetic spectrum, and this evidence kind of suggests that the dust is composed of silicates, graphite, and iron, but we're not entirely sure yet. We also have clouds of molecular gas. Sorry, there's no pictures. Aptly named molecular clouds, because atoms tend to combine into molecules at cold temperatures. These clouds tend to be dark, dense, and cold. We find them near H2 regions like the Orion Nebula. They average a density of 1 billion molecules per cubic meter and can range in a mass from 1,000 to 10 million times the mass of our sun, but it's spread across tens of light years, so they dwarf the Emission Nebula. Of course, it's still mostly molecular hydrogen, with a tiny percentage of molecules like carbon monoxide, hydrogen cyanide, ammonia, water, methyl alcohol, formaldehyde, and dozens more. So we detect them using radio telescopes typically. And then, between all this dust, gas, and molecular stuff, is even more hydrogen. Some of it hot, most of it not. The cold hydrogen releases very faint energy, which shows up as a spike in the 21 centimeter line, so kind of right there. And this says the radio spectrum. So we use radio telescopes to try and find that stuff. If we draw our perspective out even further, we see the Milky Way galaxy as a whole. billions of stars and solar systems with their own planets, asteroids, comets, etc. Supernova, gas, dust, molecular clouds, all of it. About 95% of the stars in our galaxy can be found in the galactic disk, which is nice and flat, typically right there. The bright parts are stars, the dark parts are the dust. But this disk is not uniform. Instead, it has spiral arms, as you can kind of tell from this picture, and it has a bulge in its center. Astronomers have observed that there's probably something incredibly massive and compact in the center. We'll call it, say, a supermassive black hole with a mass of 4.5 million times our sun. Black holes are very complicated creatures with immense mass but no atoms, so they kind of exist in a realm all their own. Surrounding our black hole is a ring of molecular hydrogen and a lot of it. But not all the matter in our galaxy is found in the galactic disk, because the galaxy has a halo above and below it, which contains globular clusters like this one over here, and just lonely stars. The problem with the astrophysicists have been kind of dealing with for a while, though, is that the estimated mass of the galaxy is about 10 times more than what we can see is there. So this is called the dark matter problem. There's no dust in the halo, which is where we think that dark matter might be, but they have found hot gas. If the gas halo of the galaxy is equivalent to the rest of the mass of the galaxy, we might be on our way to an answer. Otherwise, up to 85% of the matter in the universe is something that we've never encountered before. It's not on the periodic table. We don't know how it reacts with light, none of that. Finally, we get to the space in between once again. Because as special as our Milky Way is to us, it's not alone. There are countless galaxies in the entire universe, and they're spread over unimaginable distances. So while we've talked about interplanetary space, which is relatively dense compared to interstellar space, intergalactic space is different. Studies seem to show that galaxies are somehow connected by filaments of plasma. So you'll remember that's ionized gas. In between these filaments are, oh yeah, that's hydrogen plasma. Sorry, more to be specific. In between these filaments are gaps, as you can see. So when I was looking for a description, they kept mentioning kind of foam or Swiss cheese with like more air than cheese, but I think it looks more like a spider web, to be honest. But who am I to say? It's all very theoretical and mathematical anyways, but then kind of most of this talk has been, and I hope that you can kind of tell that it's a lot different than just hydrogen out there, and if it is just hydrogen, then it's a lot different than just, you know, plain hydrogen, because it comes in all different forms. But overall, I learned quite a lot in this process of learning this presentation, so I hope you took something interesting away from it too. Any questions?
Thanks, Sarah. That was great. Okay. Hello. As I was saying earlier, my name is Brendan. I will be your host this evening. We just saw Tara give us a great presentation on composition of the universe. I will be walking through some announcements, Brian will do a what's up for us, Ian will do a what's new, then we will have our refreshment break, and then you'll get to hear me talk about a bunch of history. Doesn't that sound exciting? Do we have anybody new out tonight? Hello. Hello. Welcome. Thanks for joining us. Council members, can you raise your hands? Hey, okay. New people, meet council members. Council members, meet new people. We have name tags. So you guys can hang out for refreshment break. Okay, so we got a lot to get through. But I wanted to let you know that I really regrettably missed. So we did the Tales from the Eclipse last month, and Gail sent me one, and I totally forgot to put it in the presentation. I had so much input, and I feel really bad. So if everyone's okay with it, I just wanted to throw this in just to make up for that. So Gail, I'm really sorry, but here you go.
Very good, Gail.
Well done. Thank you. Cat jokes, etc. Okay, so into announcements. Public outreach. I was contacted recently by the Wingham Colony School. It's about a 45-minute drive out of the city. They asked us to do some, if we could bring our telescopes out. Right now, I've offered to just go out and help. We tentatively scheduled for the 24th to 25th, depending on weather. If you are interested, let me know. There's not going to be a ton of people. I think it's only about 30 people or so. Theoretically, I could do it by myself, but I'd appreciate some company and maybe a hand. Another telescope would be great. But yeah, if you're interested, let me know. They're offering to cover the gas to get down there. So yeah, come talk to me at the break if you're interested. There is a mini star party happening tomorrow night, although weather outlook is not great. But this is actually, I mostly wanted to talk about this because this is something that the club's been working on a little bit. There's this Nature Conservancy of Canada site near Tolstoy, and we've actually been working with them as part of our ongoing Dark Sky Preserve initiatives. So this is kind of a way to, so they're pretty excited about the whole situation with us, having telescopes and wanting to preserve the night sky. And we're pretty excited about them being excited about that. So we've been building a relationship with them. There's a whole bunch of people in the club that have been involved in this. But if you're interested, feel free to talk to Dennis at the break about it. He's up there. We are going to be involved in another photo exhibit at the Blankenstein Gallery. This is located at the Millennium Library. This will be on display sometime in April. And I don't know if Ralph's here tonight. He's coming? Okay. So feel free to talk to Ralph, or just come talk to me about it. And basically what we'll be doing, sorry, I should give you more context. Basically what happens is at the Millennium Library, there is they have a little gallery upstairs. And we did this a few years back, a couple years ago. And we submitted a bunch of astrophotography. I think there were some sketches in there as well. So we got to put some of our beautiful artistic work on display. So it's another opportunity to do that, so I think we should take advantage of it. So feel free to talk to Ralph or myself about it, and we can sort through the details. You probably don't know this guy. I don't know. But Stan met him yesterday or the day before. But there was we had this scope floating around, this telescope floating around in our collection of telescopes that have been donated to us. And this one in particular was called Lynn's scope. I don't know the whole history behind it, but it had been sitting around for a while, and Council decided that, rather than just having a telescope sitting around, we should try to donate it. And Stan had gotten in touch with a school, and they were looking for a scope. So this fine teacher here has taken it into his possession, and he'll be sharing the night sky with some kids. So, yes, Stan.
Want some filler on that?
Sure.
So I met the gentleman last year at the STAM. That's the science teachers. They get together. They have a day's conference. And I talked to people. So he was interested at the time, and we finally gave this scope, Lynn's scope. It's a scope that Lynn, I forget her last name, but it's a young girl. One of her dying wishes is that she get a telescope. And she finally did get a scope. Unfortunately, she never had the opportunity to use it. The one thing about this particular teacher is he's trying to set up, he has a space sciences group at his school. So he, when I talked to him last year, he thought it'd be a great idea, to get a scope. So although Lynn never had the opportunity to see this, a whole bunch of students will now be able to see it. Just one more specific detail is that we actually gave the scope to him, not to the school. So we're avoiding all that administrative stuff. He took the scope on. I gave him some eyepieces, and he's going to be the one who's going to be running and grading it for all the kids to be able to use. So he was extremely excited. So the final point I want to make is this is something that if there are people here who want to donate scopes and want me to continue doing this outreach effort to other teachers and schools, you can let me know.
Thanks, Dan. Okay, so speaking of Stan, calendars. They're up for, well, they're not in yet.
They have not come in yet.
Yeah, they haven't come in yet, but I just want to let everybody know that they will be coming. They're like winter. They're $12. And they got a lot of pretty pictures in them, and all those pretty pictures were contributed by RASC members. So it's worth it. Stan, are you taking orders right now, or do you want to wait? Just hold on?
They'll be here next month.
Okay, they'll be here next month, so bring your money next month. Also, if, and it's not like you can limit, I mean, you could take some on for yourself if you wanted to, if you got people that you know that may like one, by all means. So, but talk to Stan. $12. We also are continuing our involvement in the Oakhammock Marsh Astronomy Night. This runs on the third Thursday at Oakhammock Marsh every month. Usually just a little after sunset until for a couple hours. There's a $10 entry fee to get into Oakhammock Marsh. That's waived if you are a Royal Astronomical Society of Canada member. Helping out. So if you come with a telescope or something like that, and you offer to help out, they'd love to have you, and they'll waive your fee.
Is that the October month?
Yeah, I don't actually, what's funny is I'm really bad with updating these slides to reflect the current month. But I'm pretty sure, hold on, let me just check my calendar.
It is 19.
Is it 19th, October 19th? That's a Thursday?
Yes.
Okay, it is Thursday, October 19th. Thank you. Telescope loans. This is Stan, you're really getting involved in this. The club, if you are a member, we have telescope loans, telescopes out for loan. One of them is our solar telescope, which also now includes a tracking mount. Kind of nice. You can take them out for 1 month at a time. Stan will take your information and go into a telescope. Stan, what's the list looking like?
I've got 2 scopes coming in today. Actually, one came in, one's coming at the end of the meeting. I've got 2 people here. Is Gretchen here?
Yeah.
Hi. And you're Dan? Okay, so yes. You'll get the one that's in the car, and the gentleman's bringing one at the end of the meeting. You'll get the other one. So that's the 2. Is Davidian here?
No, I haven't seen him.
Okay, because I thought he wanted the solar scope. If not, there is somebody else who wanted one? Oh, okay. So, all 3 scopes coming in, all 3 scopes going out.
Okay, so
just tell them, use the website.
Yep. So use the website, use the contact form, contact Stan. That's probably the best way to do it. That way he's got a record of it and he'll get you into the system. Go in the observatory. If you are a member, you get access to our observatory south of the city. It's nice. It's got a warm room. It's great in the winter. It's coming. Talk to Brian about that if you want more information. Speaking of the observatory, members observing night, depending on weather tomorrow, but our plan is to do it tomorrow night. You'll notice I got the month correct that time. It's November, right? Yeah, so if it happens to clear up tomorrow night, feel free to stop by Glen. Our November meeting. We're trying something a little bit different. We're going to have a panel consisting of some folks that I will certainly call experts. They may disagree. I will call experts. But what we need from you are questions or discussion topics. So, you ever had a burning astronomical question that you've never been able to get a stationable answer for? I'm guessing probably. I want a basic question about astronomy that you're too embarrassed to ask in public. Happens to me all the time. Is there a somewhat controversial cosmological topic that you'd like some expert opinion on? Or do you just want to troll them? Whichever. But yeah, if you are interested, if any of those apply to you and something comes to your mind within, like, from now until, like, next month, which is, like, January, right? Okay. Just navigate to, I'll have a link. I sent this link out to the whole email. I'll do it again probably at some point. We've already gotten a bunch of questions already, so I'm not too worried, but feel free to keep contributing, because the more the better. But you can go to this website, and that'll take you to a Google form where you can just submit your question. If you want to update your question, just submit it again. Doesn't matter. I see everything as it comes in. So, but yeah, feel free to go to that. It'll also be on the November meeting page on the RASC website. Cool. Okay, now special presentation time. So as part of the Winnipeg Club, we have awards to give out. We have 2 awards that we hand out almost annually. Close to annually. Semi-annually. Not biannually, that's different. Or 2 annually. Anyway, sorry. Okay, I'm going to stop making bad jokes. So, I'm making jokes. But we have a couple awards. One is the award for outstanding service, and the other is an outstanding achievement award. So, I'll start with the service award. So, and to be clear, this is something that this is determined by council. So council gets the pick. So if you want to have a say in this sort of thing, join council. Just throwing that out there. So, but for the service award, this was a pretty easy one, and we were quite shocked that this individual had not received the award yet. If I had to pick one word to describe this individual, I would probably go with dependable, which sounds a little on the light side, but I can honestly tell you, as somebody who's had to organize and run these meetings, it's really important. Dependable is an amazing quality to have. Not just that, but dependable and consistent. I think I've been coming to these meetings for probably 8 years now, and this person has been involved in just about every single one of them. In particular, he actually saved our butts back at the planetarium meeting that we did when we realized that our stuff was not going to work for displaying everything, and he drove all the way home to grab the equipment and then come all the way back to the planetarium while we did the planetarium show. Totally saved our skin. Chris, could you please come up here? Chris, for everything that you've done for the club, but in particular, everything you've done to keep our AV system going, coming out every single month, setting it up, being just the most consistent, reliable person that I think I might know in this club, I'd like to present you with the Outstanding Service Award. Okay, and now we have the award for Outstanding Achievement. So, I don't know, I'm in story mode. I'm just going to, because I'll be doing this later, I'll be telling you guys stories. It'll be fun. So several years ago, we did a dinner at Fort White, and one of the presenters was there to talk about dark skies. And one of the things that I really took away from this was that this individual was very passionate about it. I think one of the things that they said was that they really got into this and just fell in love with being outdoors and being able to just experience the night sky in its full glory. And since that time, this person has really spearheaded our efforts to get a dark sky preserve set up at Spruce Woods. So, there have been a lot of people involved in this, but there is one key person who has really spearheaded this entire effort over the past several years. We got a lot on council. We got several people actually who had nominated this individual for this. So when we reached out to the club and asked for some input, this one came up from a number of people, and I think it's a great one. So Tim, can you come down here? Now, while we've had a few hiccups in the dark sky preserve process at Spruce Woods, I have every confidence that we'll be able to work through those. And I think, Tim, you've done just an amazing job out there. So I'd like to present to you for all of your work, getting us quite possibly the first dark sky preserve in, hopefully the first dark sky preserve in Manitoba. Thank you. Okay, so now I can stop being sappy and get back to making bad jokes. Although I don't have any bad jokes to make. So, Brian, did you want to come down? Yeah, it's your turn. I do. Yep, I got it all loaded. He's just trying to show me up a little bit.
Next time I'll wear something different. Alright, and I did change it. Not September, it's October. Anyways, okay, what's up for the next guy? Good news is a lot of feedback here.
You don't stand close to the bottom.
Is that better?
Yeah, you're good.
Everyone hear me?
Yep.
Great. Alright, let's get this started, shall we? Okay, we're going to talk about what's up for the next guy for this month. Mercury. What can I really say about Mercury? It's really behind the sun. And the next week or so it'll come around the sun and be able to see it then. Venus is pretty much a dawn planet. So I really can't say. One interesting fact I kind of learned about is that it's supposed to be 200 times brighter than Mars on the 5th of this month. I don't know if anyone saw that, but Mars, pretty much the same thing. Conjunction of Venus on the 5th. Jupiter, well, it's pretty much a day planet, can't really be seen, it's too close to the sun. Saturn, unfortunately, one of my favorite planets. It's going to be setting in the dawn sky. Soon we'll miss it all together. What else? Okay, so this is kind of an overview of the planets that we have. Kind of give you an idea of what I kind of tried to talk about. And there's laser pointers. Okay, there's Earth right here. You can see there's Venus and Mars, how they line up in conjunction on the 5th. Mercury's behind the sun, so it'll be coming around here. The planets are moving counterclockwise. Oops, a little too fast. Jupiter, of course, pretty much too close to the sun. And Saturn, as you can see, it's going to be setting in the evening really soon, if not right now. Now, what's happening for October? Well, we still have a couple of meteor showers, but the big one's on the 21st. We have the zodiacal lights starting on the 17th for the next 2 weeks. If you haven't seen it, you should, but it might take a bit of a skill to look at it because it's not exactly obvious, and I'll show you why. Of course, we have the new moon on the 19th, which is almost perfect for the Orion meteor shower on the 21st. That's a Friday. I'll talk a little bit more about it. I kind of threw this in here. I thought it was kind of fascinating. We have a lot of smaller meteor showers for the month of October, and they kind of overlap. So my prediction would be, you know, almost every night you should maybe see a meteor. That's my prediction, right? Of course, I bolded the one for Orion here. So on the 21st, that +3 means that the moon's going to get a little bit bigger. And of course, that's the hourly rate for the meteor shower. 20. Some information said 15. Most of them say 20. And of course, that's debatable how much of the moon is going to really be, but if you want to debate about it, we'll talk about it when we repeat that. All right, the Orion meteor shower. Okay, so there's Orion. You can see where it's going to kind of localize, or you know, where it's going to radiate from. One interesting fact I kind of liked about it, that it's from the comet Halley's. That's the debris from it. So I thought it was kind of fascinating that we're able to see the meteor shower. And of course, it peaks on 21st of October. So that's Friday night. So that's the 20th. So starting Saturday morning, that's where you're able to see it, which is perfect because it's a weekend and weather permitting. I pray to God it is. I think it's going to be cloudy by the looks of things with our luck. Everything else, that we might be able to have a nice little meteor shower. All right. Now for the zodiacal lights, this is just a lot of information here, but I'm trying to explain that it's the planetary dust. Of course, how it looks like a radiant solid pyramid. I got a nice picture, thanks to Kevin. Follows the elliptic planes of the sun. And of course, the geometry is right to be able to see it, providing that you're in a nice dark area. What else am I going to say? Okay, now this is just a little bit more information on how to see it. Make sure you have a dark area to go to, maybe like Leap, for example. And of course, I keep mentioning this, don't be surprised that even the more experienced astronomers have not even seen this. But I was able to saw it the first time around in Arizona, thanks to Jay and Stan, heading off to the side of the road. Okay, now it's going to happen for the next 2 weeks, and that's it. After October, you're not going to be able to see it until the spring, but it's in the evening this time, or next time. Okay, thanks to Kevin. Thank you. This is how it looks like. I brightened it up a little bit because I was kind of worried about if it's going to actually see over the screens. So you can actually see it here. Here's the pyramid right here. Everyone see that? So that's the path of the sun right here. That's the Milky Way. And I'll show a next picture of it right here. Again, I kind of brightened it up a little bit. There it is, right there. Got the lights. It might be a little subtle than that, but if you have a really good dark sky, you'll be able to see it. There's Orion right here. So what time was that, Kevin?
4 in the morning.
4 in the morning, okay. I guess I was asleep by then. All right. You went by yourself, did you? Or did you go by yourself?
Yeah.
Okay. All right. All right, let's move on. Okay, comet chasing. Now this is comet, how do you say it, assassin? You know, you haven't started. I know. Thanks to Kevin, I'm calling it assassin. Okay. Okay, it should be visible for a small telescope, but I haven't really observed it myself, but I do have a picture. There's Perseus, the constellation, so it's right about here. It's going to be moving upwards, but it's moving away from the Earth, unfortunately. Okay, now what time next? Okay, that's the orbit of the comet. There's Earth. It's actually moving away from us in this direction right here. Unfortunately, what else do I have for the comet chasing? This is the picture of Kevin. Thank you again. It's right about here. So it's actually, it should be pretty bright to me. It's kind of small, right?
What the other comet?
What?
There's two comets.
Right here?
Yeah.
Yeah, that's what I kind of thought. Is it Comet Johnson or something? Or?
Johnson.
Is it Johnson?
Pan-star.
Pan-star, okay.
They're at 61.
But like, I thought the magnitude was like 11 or something?
12.
12? Okay. Because I thought it was just too dim to actually see it. So that's why I didn't mention it. I thought,
Killed two birds with one stone, went out and they shot both together.
but that's pretty small actually.
It's
It's pretty small. Anyway. And what do I have? That's it. That's all I have for what's up. Hey, that's my cup. Oh, good.
If you were the owner of a white mug with green and purple, no, green and pink stripes on it, whatever, Brian just stole it.
Star Party.
Sure,
Yes.
sure.
It's left over from the Star Party.
Okay, so next we'll have Ian with what's up, or sorry, what's new in the science of astronomy. It could also be what's new, it's not a good. So, actually, what we're waiting for Ian just to get his, well, he has to cleanse the area of the PC contamination in order to get his MacBook set up. There's some form of ancient ritual that needs to take place first. So while he's conducting that, I just want to let everyone know that we have free copies of Sky News to hand out. And you can take a bunch of these if you want. I usually like to take a few just to bring by work and, you know, drop on the table. If you know, actually somebody once suggested heading out to some dentist office or something like that and just dropping them off there. So yeah, feel free to come pick them up. So they're down here. We've also got a few other magazines here. I think they're free for the day as well. Yep. So we got some other magazines, Scientific American. There's America's Eclipse 2017. I missed it? Yes. Yes. To be perfectly, yeah. Jay mentioned a good thing. I mean, you already, if you're a RASC member, you already get this. So I don't know why you pick any, but they're intended for non-RASC members. So I mean, that's what you should be thinking. Also, if you're a RASC member and you're not getting Sky News, contact National. So, show of hands, who knows the story of the discovery of Neptune? Few people? Okay, good. I'm sorry for the people that already know it, but yeah, hopefully I'll throw something new at you.
So everyone can hear me fine. Good. All right. First a little bit of news. Are you up for a pop quiz? This was, of course, a very exciting event. Can anybody name the people? Which one? Right, okay. Okay, no, it's not. All right, so we'll put you out of your misery. Okay, there's Weiss, Barish, and Thorne. Okay, and of course they shared the Nobel Prize in Physics, and basically it's for their decisive contributions to the LIGO detector and the observation of gravitational waves. Okay, and we'll come to why that is so important. The prize is split, half, quarter, and quarter. It turns out Reiner was responsible for the business of the actual technique, the interferometric technique. What was with the audio?
Just adjusting.
Just adjusting. Oh, I see. Okay, good. And Barish, an experimentalist. And of course, you're probably familiar with Kip Thorne from his background work for the movie Interstellar, right?
Yes.
All those special effects. Okay, actually have some, presumably some basis in theory, if nothing else. And if you really want to know what they look like, there they are. So, just a little bit of background, because my second news item actually has to do with the actual use of this instrument. What you're looking at is an interferometer. Very simply, what you do is you bounce light around at each of the arms, you make them interfere with one another. It detects the tiniest movements, is really what it does. And the important thing about, well, these are big, all right? The arms on these are 4 kilometers each for these particular detectors. And so just a slight movement, presumably as the gravitational wave passes by. You shorten one arm with respect to the other, right, and you actually detect that movement. Of course, you can only do that if your instrument is sensitive enough to do that, and you've got rid of all the noise, like the sort of the trucks traveling by, and all those kinds of things. I'm not sure if it's sensitive enough to get footsteps, but anyway, what you're really interested in is getting rid of all extraneous sources of a possible signal, right? And basically that nice little curve that you see up there with the spikes gives you some sort of measure of how good this instrument is. Right? So it's, and it basically does it over frequency. Okay, so you can see that just look at the numbers, really tiny numbers, okay? And in a moment, when I come to my second piece here, you'll see what that actually means when we sort of try to actually use this instrument. So this is the cosmic get-together of a couple of black holes. Okay, because of course theory predicts if I've got some black holes coming together and merging, I'm going to have a source of gravitational waves, and that's going to propagate through space, and as it passes through the Earth, we're going to be able to detect them with these particular detectors. It turns out that there's a third detector, okay, the Virgo detector, okay, that's located, well, in a moment I'll come to that. And that's added to the mix here. Basically, you see how not quite so good it is, right? But there's actually an advantage to having a third detector. Right? This one, curiously enough, well, I think I like this. It's located near Pisa, in Italy. And what's famous about Pisa? That tower. And
Cannonball.
and gravity. And gravity, right? So I think this is really apropos to have this detector located in this particular position. So you've got 3 basically detectors, and you get this beautiful signal down at the bottom. The other stuff you really don't need to worry about too much, other than the fact that what we're really interested in is maybe that top line that gives you the signal-to-noise ratio. In other words, this is the kind of signal that you're seeing in the various detectors compared to what you're just sort of picking up, okay? You know, think of the other stuff as static, all right? Essentially, that's what it is, all right? It's just noise there that somehow or other you've got to be able to detect the sound, if you like, of what's happening above it. And so we actually see, okay, nice signals from there. So we actually did detect, presumably, an origin. So what's the advantage of having a third detector?
Find where it came, noise came from.
Triangulation.
You basically can triangulate on a 3 triangle, right? Well, and so it turns out now that instead of having this huge swath of sky, which is the possible origin over here, for the event, you can actually narrow it down. And I have very conveniently thrown my cursor right in front of the scale there, but that's actually 10 degrees of the sky. All right, so you've gone from basically almost, you know, a huge strip of sky right down. And this gets astronomers really excited because now we're entering the era of gravitational wave astronomy for real. Means you can start looking for objects now in all the wavelengths that you might like. And so that's what got people really, really excited right about now. So, this is what's been happening over the past little while. We've got these kinds of signals, we've got these kind of events that are sort of happening. And at the moment, it seems like we're limited to black holes. Right, but there seems to be maybe some scuttlebutt that might be able to do better than that. And of course, that's gotten a lot of us excited as well. All right. Well, you've heard about the, let's see, the missing matter problem, right? How many people have heard about the missing baryon problem? Yeah, everybody gets sort of thrown into the exotic stuff all the time, you know, dark matter, dark energy. Well, there's just some plain old matter that's missing, okay, from the theoretical predictions. And if you have a look at, you know, you've got some fairly good models, good observational evidence that sort of matches up, but we also have, there's not enough normal matter, if you like, baryons. Think of, you know, things like hydrogen atoms floating around, stripped of the electrons. You've got a good introduction to that from Tara earlier on, right? All right, so how do you go about detecting those kinds of things? And so something rather exciting has happened over the last little while. And of course, a little bit of cleverness, and which is what you expect of astronomers, right? You know, astronomers have to work really hard for any information they get, all right? And they do work hard. They enjoy what they're doing, obviously, otherwise they'd probably never stick to it. So here's a model, okay? So we've got, as Tara pointed out, you know, stuff is interconnected. And so what actually two groups decided to do was to have a look at this in a little bit more detail. And again, they exercised a little bit of cleverness. There's a group that's based actually in UBC, so we've got Canadian content in this particular news item, and another one in Glasgow. I think it was Glasgow or Edinburgh. And they did something rather interesting. One of the things that we have available to us these days is lots and lots of data. And a lot of you are familiar with some image processing techniques where you stack images, right? You stack images so that you can see more detail. So what these people do, the two different groups, is they actually had a look at pairs of galaxies. Okay, and from actually two different surveys. And this particular survey was from the Sloan Digital Survey. And what they did is they had a look at galaxies which have reasonable amounts of separation in the sky. And what they were interested in, was there anything really in between? There's a strong suspicion that what you have is you've got hot gas, but unfortunately, you know, it's not enough of it that you can detect it, say, through X-rays and things like this. So what are you going to do? Well, what you do is you use the early universe radiation that's passing through here, through the space between these galaxies. And there's an effect which has a very fancy, my Russian's not any good at all these days. So I'll just call it the ZS effect. You can see that there. And what it means basically is that photons scatter off the material in between. And that results in a dimming between the galaxies. So you have to do a lot of work. So in this particular instance, these guys, okay, looked at, what was it, 260,000 pairs of galaxies. They had to meet very specific criteria, okay? And of course you have to do a little bit of modeling so that you can subtract the effect of the halos out and see what's left over. Presumably what's left over then is this actual hot material between the galaxies, and you can get some indication of the density of the material in there, and therefore some estimate. And so what happens is somebody says, missing baryon problem, gone away. So this is really quite an exciting result. And this is the other one. They only did 1 million observations. All right, so the fact that it was done independently, 2 different catalogs, okay, leads us to believe perhaps that this problem has gone away. Okay. The next is a rather interesting news item, in a way. This person is deceased. Oh, I see. Yeah. Okay, 1997. Okay. And has, if you like, become more generally recognized for her contribution to solar observing. And she did a lot of sketches. She started out as a young woman. Here, I think this one's in 1951. And the other one probably about 16 years later, I think it was. All right? And essentially using the same instrument. Right? She got involved basically as an observer at what is now the National Museum of Nature and Science in Tokyo. Okay. Always worked as an amateur to some extent, and also been a professional staff member. Did a lot of outreach to do with astronomy, but essentially this was the mainstay of what it was that she was doing all the time. Used the same instrument. How long did she use it for? Quite some time. All right? Wow. And she did something like about 10,000 solar sketches. So for the sketch artists among you, you've got a little ways to go, I think. And so she was very diligent about it. And these are the kinds of sketches she produced. And you can access these, because they're all digitized now. The website is indicated up there at the top. This was, I think, the largest sunspot group of the 20th century. This particular group over here. And here she observed a white light flare. And she basically, she was a meticulous observer, as you can see, made some notations along the way, and produced her own butterfly diagram. So that's all her own data that you actually see there. Okay. So she was involved in keeping sunspot counts as well. The significance of her work scientifically is the fact that you've got a single observer, basically the same instrument over a long span of time. And that what that allowed people to do then is having that as, if you like, a fiducial, a reference. They could go back through historical records, okay, and basically normalize a lot of the other things, right way back to when sunspots were observed and recorded early on in the 17th century. And from that, of course, you can tell what the behavior of the sun is over that period of time. So her data has made its way into any number of scientific papers and all along the way. And so just recently by the Geophysical Union, she was, if you like, recognized for her long-standing contributions. She was recognized during her lifetime, should point that out, and certainly recognized as one of the premier solar observers of the time. A little bit of local news. All right, it turns out that University of Manitoba and the University of Toronto recently received a Canada Foundation Innovation Award for, I think, a few $1 million, to basically to have a look at a lot of the raft of radio data that is now pouring in and making images. So Dr. Sandy Harb here, I think, and Dr. Steffi Baum are the leaders at this particular university. And that brings me to a close.
Some of the history of the planetarium and the astronomy resources at the university, and then feed that into how it pertains to things that are modern and recent. And so the first one will be, I think, November 1st, the first Wednesday of November. And so you're all welcome to attend. It's free. It's open to everybody. So if you're interested, or if you're interested in volunteering, please reach out. And we'd love to see you out. Thanks.
So, for people that didn't read their email or didn't read the website, this talk is, well, so I guess I'm gonna take like a very small subset of what Kara did and expand on it. So the part where she covered the solar system, I'm not going outside of that. And so what I'm intending to do is describe how we came to our current understanding of the planets in our solar system, which might sound a little bit of a broad topic, a little dull. So what I've chosen to do mostly is focus. I'm going to spend a lot of time focused on the discovery of Neptune and the story behind that. It's pretty fascinating. And if you've heard it before, I will hopefully be able to interject at least a little bit of additional color to the story. So we'll see where that takes us. But let's break it down. What to expect? Science. I will be talking about science. But I'll also be talking about history, and a lot of it. Expect lots of old white dudes. This is just a natural consequence of European civilization. Thankful white dudes. Bad jokes. Good jokes. Bad jokes that were in the good jokes. Nothing well good. Deal with it.
Sad.
Yeah. Well, I mean, not entirely nothing about Pluto, but I couldn't quite fit it in. So, bear with me as we entertain a purely hypothetical situation. Pick your favorite captain. I mean, we all know which one is the best one, but pick your favorite.
You're missing one.
Oh, right, yeah, new show. Okay, so, well, you know what? I actually made these slides, well, this slide I made before it. Anyway, pick your favorite. Now, it's Star Trek, right? So you're going to pick your favorite anomaly. Could be a transporter malfunction. Could be this weird purple gas cloud thing. Could be an angry alien. Or whatever the heck is going on here. Everyone's selected their favorite, anomaly, right? Supposed to be imagining things here. So, something anomalous happens and you're teleported to another world, right? A very unfriendly looking world. So, we're trapped on this world. We don't know where we are, right? But we're astronomers, right? Like we can look. What is the very first thing we're going to do? Right? We're going to look up, right? We're going to look up into the night sky, and we are going to try and learn as much as we can, right? Because that's what we do. Yeah, I mean, yeah. Let's assume you've got your rations with you. Okay. You guys wait till I get to the history part. So, you look up on the first night, and okay, it's like, okay, there's some stars there. That's the brightest star there. That's a big, bright one. Okay, cool. Okay, well, that's interesting. Don't really see a lot that I recognize, but that's okay. We'll come back the next night. Second night. Hold on a minute. Where did that guy move? Okay. Yeah, that thing definitely moved. Okay, that's interesting. So let's just keep an eye on it. Right? Oh, okay, it's continuing to move. We keep moving along. Night after night it moves, and oh hey, there's this other guy that just popped up out of nowhere. Cool. What did we learn?
Clear skies?
Jay's getting hungry. Yeah, also, you have a remarkable observing condition, right? Yeah. You throw a purely hypothetical situation at people and they only want reality. So, what do we know about them? Likely, these are planets, right? So how do we know that? Well, they are moving much faster relative to the background stars, right? And what that tells us is that they're close to us. And what that means is that they are likely planets. Now, I mean, I'm making a bit of a supposition here, like these, depending on the solar system that we're in, these could be, I don't know, big, oddly shaped asteroids, whatever, kind of thing, right, that just happen to reflect enough light that we can see them. Who knows, right? But for the most part, you can just say that, these are planets, right? And as most of you, I think, have heard this, planet is derived from the Greek word for wanderer, and that is how we came to understand them, right? But how does this help us? It doesn't. It's a hellish landscape unsuitable for human life. We ate 7 days of food rations and we're dead. So But we've got Venus, Mercury, Jupiter, Saturn, and Mars. Okay? So back in ancient times, this was what we knew of the planets. This is what we knew that we had in our solar system, right? And that was the extent of it. That was as far as our knowledge went, right? But it was known all around the world. The Babylonians, the Greeks, the Romans, the Indians, the Chinese, all of the astronomers around the world knew that these bodies were special, right? And over the years, Kepler, yada yada yada, Newton, yada yada yada, and then we get to Herschel. Okay, so in that yada 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 is basically we figured out that these are as we drifted toward heliocentrism, we knew that these bodies were orbiting the sun and that they were planets like ours-ish, right? So that's what we knew about them. We knew that their orbits followed ellipses and that they were orbiting the sun. So this is all really good information. Now, William Herschel comes along in 1738. Well, he was born before that, but he comes along. He comes along, and he's an amazing astronomer. He did a ton of incredible work, which we'll get to in a minute. But some people probably know this, but I don't know if everyone does. He was actually a fairly prolific composer. So while I'm describing his life and however much longer this goes for, I'm going to play you some of his music because it sounds classic. Can you hear it? Yeah. I want to keep it a little bit quiet just so it doesn't overpower, but notes of it will spring forth as I describe his life. So William Herschel. Much of his work over his 83 years, he lived quite a long time for a guy of his era, was done with his sister, Carolyn. And she was actually notable for the discovery of several comets, so she was quite involved in that. This will regrettably be the only woman that I talk about tonight, so apologies for that, but that's what we get with old white males. Now, Herschel has a massive list of accomplishments. He discovered Uranus, spoilers. He discovered Uranus' moons, Titania and Oberon. He discovered Saturn moons, Enceladus and Mimas. He discovered infrared radiation. He discovered the seasonal changes of Martian polar caps. He published catalogs of thousands of deep sky objects. He identified 1,000 double stars. He constructed more than 400 telescopes. And he also achieved the ultimate in aperture fever. This is the 40-foot telescope. Construction on it was completed in 1789 and was the largest telescope in the world for 50 years. Pretty good work. Little, big, but, so who was Herschel? Well, he was born in 1738 in Germany, and ended up seeking refuge in Great Britain during the 7 Years' War, which I will not describe to you in any sort of detail. Interesting stuff, but I won't talk about it. And then, kind of by chance, he became acquainted with an amateur violinist who also happened to be interested in astronomy. It's kind of what sparked this whole thing, really getting into it. And then by 1774, he began his own astronomical journal. So, this is a recreation of one of Herschel's telescopes. What's remarkable about Herschel is that his optics were actually quite good. He spent a lot of time on the process of making telescopes, and was able to develop some very, very quality stuff. And this, in March 1781, is what actually really helped him to discover the planet Uranus. So he was looking, and so he was, like astronomers at the time, most of them were looking for comets. That was the big deal, right? So looking, these things were just passing. They were, things had drifted more into the realm of science at this point. They didn't go so much care too much about the importance of doom or whatever kind of thing. But finding comets was still a big deal at the time, right? And so one night during his search for double stars, Herschel noted that when he magnified the field of view with his very good optics, that one of the stars actually began to appear as a disk. And that disk was actually the planet Uranus. So Herschel recorded in his journal, in the quartile near Zeta Tauri, either a nebulous star or perhaps a comet. I looked for the comet or nebulous star and found that it is a comet, or it has changed its place. So like we were talking about, he went out night after night after night and kept observing this object. And that's how he was able to fully determine it. Johann Ellersbode, I think this is old white dude account number 2. I'm not going to try and keep track of that. He described, famous for Bode's law, which we'll talk about, he described Herschel's discovery as a moving star that can be deemed a hitherto unknown planet-like object circulating beyond the orbit of Saturn. So there was a lot of, it didn't take very long to reach some consensus that that William Herschel had truly found another planet beyond Saturn. So this is pretty big, right? Because up until that point, the only thing that we really knew about were the planets up to Saturn, which we had known about for thousands of years, and comets, which we'd also kind of known about for thousands of years, not all of them obviously, but just the presence of them, right? So this was another planet. This was a big deal. Now, what's kind of funny and sad about the whole situation with Uranus is, you can see the planet Uranus with your naked eye. It is that bright. It's actually not, I mean, it's a little challenging to find, but it is visible. And you had astronomers out there who were cataloging things like crazy in the night sky because they were trying to find comets. So they were comparing all the time. They were, comparing to their previous records and everything like that. So there were a few people that had actually seen Uranus and missed it. John Flamsteed, he observed it 6 times and actually cataloged it as 34 Tauri. So there's actually a star chart that he had built, a star atlas, and he cataloged it as 34 Tauri. This is a rather famous one, Pierre-Charles Lemonnier. This poor guy, he observed Uranus at least 12 times between 1750 and 1769, including on 4 consecutive nights, in which he should have been able to see it in some motion. Although the optics at the time were not that good, so there's that. There was actually, while I was reading up on this, there were some criticisms of Charles Lemonier's record keeping. Apparently somebody found one of his records that actually had Uranus on it, and it was on the back of a perfume hanky or something like that. So not exactly the greatest of record keepers, which I think is somewhat evidenced by that. So, like I said, this is a big deal, though. This was a really big deal in science. And so, what was the impact of the discovery? So, we'll try to summarize that a little bit. Herschel. Okay, so I talked about how he built like 400 telescopes and all that, kind of thing, right? Well, he did that because he was appointed the king's astronomer. He was given the resources and time to really, do that. It kicked off a massive hunt for other planets. This totally opened our minds and broadened our horizons to being able to, the idea that maybe there are other planets out there beyond what we had known for thousands of years, right? Really kicked that off. It also launched an effort to plot Uranus's orbit, which was a very mathematically challenging thing to do at the time. So, we'll dive into each one a little bit further. So what was the result of Herschel becoming the king's astronomer? We talked about that already. The man became rich. He got to build a giant 40-foot. Now, the hunt for, so this did kick off a hunt for more planets. At the time, prior to Uranus being found, this law was derived. By these 2 astronomers, Nicias and Bode. Let's call it Bode's law for short. What it predicted was that the planet's orbit at a consistent distance from the sun. Now, not the same distance, but that it follows a mathematical pattern, right? It follows a I want to say rhythm, but I'm just listening to music right now. We'll just see. But basically what happens here, so the idea is that you have this formula, right? Pretty simple formula, but you take m, where m is the number of, where it is the index of the planet. So if it's 0, you plug it into there, that gives you 1. Multiply that by 0.3. 0.3 plus 0.4 is 0.7. Right, so that's, sorry, so 0 would be 1.3. Anyway, sorry, I messed this up. Yeah, anyway, sorry, just ignore that for a second, sorry, okay. Anyway, the point is that the distance, what this does though, is it gives you the predicted distance of every planet in the solar system known at the time, with one key exception. There was a gap, okay? So, there was this missing, we had this 1.6 for Mars, we had a 5. These are astronomical units, which is the distance from the Earth to the Sun. We had 5.2 for Jupiter and 10 for Saturn, but there was this 2.8 number that should have been there, and there was nothing there. Then Uranus was discovered. And what that meant, and when Uranus was discovered, when they started plotting out its orbit, they found that it did actually match up very well with Bode's law. So there must be something there, right? And this really got people looking for objects in that region of the sky. Well, not that region of the sky, but people were intent on trying to find something there, right? So rather than just hunting comets, this was a big push, right? There's a whole bunch of stuff we can talk about with asteroid discoveries. Jerry actually did a very good talk on this a while back, but so cut that off a little bit. But the big ones were so in 1801, it's seriously discovered by Giuseppe Piazzi. 1802, Pallas was discovered. Then 1804, Juno was discovered. 1807, Vesta was discovered. This fit in really nicely with Bode's law. Right? So kind of cool. We filled a nice little gap there. The only thing was that it didn't take it took some time, but it didn't take too long to realize that these things were not that big, and there was something different about them, right? So Ceres is the biggest one, and even compared to our moon, it's quite small, right? So these were the asteroids of the asteroid belt that we were starting to find. And as time went on, about 40 years later, we started to kind of realize that, okay, these probably aren't really planets, as we would define them, although there was a lot of debate about that. But with the discovery of Pallas, Herschel, who great planet astronomer, they resemble small stars so much as hardly to be distinguished from them, even by very good telescopes. He's not that impressed. So, but we had the planets, we had Uranus, and we had the asteroid belt. So, the subsequent effort to start plotting Uranus's orbit started facing some challenges. And to explain some of these challenges, we have to go back to the what's called the Great Jupiter-Saturn inequality. So this was a problem where Jupiter and Saturn's orbits, we knew that they should be elliptical, but they weren't quite perfect. Given the opposite of time, we could tell that something was off about their orbits. And we had to come up with some new math to really explain it. So enter Pierre Simon Laplace, brilliant mathematician, did a whole bunch of amazing stuff, but for the purpose of this talk, this is all I care about. So Newton had shown that the orbits must be elliptical, right? So this is mathematically proven based on Kepler's laws, yada yada yada. Laplace showed that this doesn't necessarily apply in a multiplanetary system. Because if you have two big objects, the law of gravity dictates that they should have some effect on each other, right? So what you get are orbital perturbations. I'm going to say that word a lot and probably mistake it several times. So what happens is, so if you imagine the inner being Jupiter and the outer being Saturn, what will happen is, so this takes longer to go around than this, right? So Saturn takes longer to go around than Jupiter. Saturn, Jupiter, longer, shorter. When this will then make more orbits than this. So when this passes this, some gravitational effect and affect its orbit. Similarly, as it comes by on this side and shoots past this way, it will also have an effect on its orbit. Right? So they realized that, okay, we can actually, now using this new math that Laplace has given us, we can actually much more properly determine their orbits. This is great. Now, we get into Alexis Bouvard. He was interested in plotting Uranus's orbit, but he was running into a number of issues. He started to take the ancient observations. So this was, I mean, one of the cool things was that they were able to go back through the records and they realized that guys like John Flamsteed and Pierre Charles-Lemonnier had missed it. So what they did was they went, but it was still valuable data because it showed where the planet was located at the time. So Bouvard tried incorporating these data into his calculations. They didn't add up. So when he tried plotting its orbit, he was encountering errors of up to 120 arc seconds, okay, which is pretty significant. It's quite huge. So he threw them all out. He said, "There's no way. This guy kept his observations on the back of a perfume hanky. There's no way that this is accurate, right? He just must have been completely out to lunch." But modern day observations showed errors of up to 10 arc seconds, which is still quite significant. So, because of that, he began to hypothesize that there might be an eighth planet. There might be some affecting, something out there could be affecting Uranus, right? And its orbit, similar to how Jupiter and Saturn have that effect. So, another old white dude to introduce. This is George Bedell Airy. He was the Astronomer Royal from 1835 to 1881. Basically meaning that he was the head honcho of the Royal Astronomical Society up in Britain. So this is a very British man, which you'll see a lot of. You'll hear a lot from this guy. He goes on quite a bit. In his 1832 report on the progress of astronomy, he wrote, "A singular difficulty occurs. It appears impossible to unite all the observations in one elliptical orbit." So guys like Airy were looking at this and saying, okay, like there's something up here, right? We're trying to plot Uranus's orbit. We've seen enough of its data. We should be able to figure out its orbit from the data that we have. What's wrong? Propose explanations. Commentary impact. Right? We got hit, right? That might throw it off, right? One of the problems with this was that it wouldn't account for the ancient observations because it would have had to get hit twice, right? So it didn't really work out. Uranus's orbit passes through an undetectable resistive medium. Never heard anything like that before. So yeah, that one wasn't looked at too highly. Yeah. I wasn't going to say it. Or possibly an unseen, ludicrously sized moon. Right? Maybe Newton's laws of gravity are wrong. Huh? Right? Who knows? Or maybe it's another planet. Now, at the time, though, most people were still pretty skeptical of the idea of there being another planet. The idea was not taken too seriously. Around that time, George Bedell Airy actually wrote this, and like I said, the man goes on. It is a puzzling subject, but I give it, as my opinion, without hesitation. This is the crap I had to read while I was researching this. That it is not yet in such a state as to hope to give the smallest hope of making out the nature of any external action on the planet. Basically, it's a long shot. Okay? So he was quite skeptical at the time. Even more to that point, he said that even if there was one, he didn't think that it would be easy to detect, and that it would take many, many revolutions to be able to determine that. In fact, now, Uranus takes 84 years to go around. So successive revolutions, we'd be talking like, around this time in order to be able to do what he's claiming here, unfortunately. So, not looking good from his perspective. So now we introduce another old lady, John Couch Adams. He's an interesting character. Talk a lot about him over here, but just to give you a little bit of an intro. He was rather reserved, mostly, very much cared about mathematics and astronomy, but was kind of your almost, stereotypical kind of like standoffish, brilliant person who just, didn't engage with society, as well. Like there was nothing really terribly wrong, but just that he didn't necessarily engage with people all that well, and that contributed to some of the difficulties that he faced. But he was born in 1819 in this little place called Lanneast in England, down in Cornwall. He was the oldest of 7 children, and early in his life, like I was saying, he was something of a math prodigy. He took a strong interest in astronomy around the age of 14. One thing that I thought was really cool, you might be wondering, why is Brendan showing you the eclipse from 1835? That's not something we can go and see. But there's something interesting here. This actually skirts this eclipse. This partial eclipse actually skirts his, like where he was, and at the age of 16, he actually predicted how much coverage this solar eclipse would have, which is pretty astounding for a 16-year-old. So he definitely knew his stuff. He ended up going to Trinity College, St. John's College, and that's the view of Trinity College. And so this is Cambridge University, and just started doing the whole math thing. So he went to school, learned a lot of math, and really just got into doing the mathematics of astronomy. He also, because he was at Cambridge, came across George Bedell Airy's report on the progress of astronomy. Now, this is the one I was talking about earlier. Now, keen observers will note that this is not actually the report on the progress of astronomy from 1832. I tried to find it. I swear, I tried to find it. I could not find it. Sometimes I love the internet, but sometimes I really hate it. Sometimes finding old stuff on the internet gets you the wrong results. Carrying on. But anyway, the point of this is that he found this report on the progress of astronomy. And this inspired him. He read it, and he read about the misbehavior of Uranus, and realized that there was a mathematical and astronomical challenge here that he could really sink his teeth into. In fact, he said, you see, Uranus is a long way out of his course. I need to find out. I need to find out why. I think I know. So, Adams sets out to find an unseen planet that could account for the anomalous motion of Uranus. So, going back to the Jupiter and Saturn thing, this is effectively a problem of determining inverse perturbation. So, in the Jupiter and Saturn situation, where you're trying to plot each one's orbit, right, you get to observe both objects, right? So it's easy to account for one affecting the other and the other affecting the other. In the case of Uranus and what was to be Neptune, he didn't have that. He had Uranus, sure, right, is being affected somehow and is affecting something somehow, right, is what his hypothesis was, but he had no way of determining. That was his goal. He needed to figure out where this thing was based on the effect that it was having on Uranus. So he was going to mathematically figure that out. Challenging. Because the problem is, calculating the true eclipse depended on knowing the perturbations caused by the unseen planet. Also, those perturbations could only be calculated if the true eclipse was known. Right? There's a few, that's some basic algebra, there's a bit of a problem here, right? Like I said, he was a mathematical prodigy, and he sat down and really started to chew through the math. So these are actually Adam's equations. Now they are just the general ones. The thing to keep in mind here is that I'm going to call this a calculator. It's a very simple thing that it does. Okay, this is my cell phone. He had no way of doing these calculations, you know, via any kind of technology at the time. I mean, he had to sit down and crunch numbers, right? The really rich old white dudes at the time had people to do that for them at least. But Adams was basically stuck doing it by himself, and so simple predictions effectively would take him months and months and months at a time to be able to find. So, but here's what the solution provided. Corrections to Alexis Bouvard's tables. So he went back and looked at Bouvard's tables and said, hey, if I figure out the perturbations that are happening on Uranus from this unseen object, I can actually go back and correct for Uranus's misbehavior in its orbit. Kind of cool. And 2, he gets the orbital characteristics of the unseen planet. Right? So this actually does 2 things. It determines Uranus's orbit, nice and clean, and it also predicts where the unseen planet would be. The only thing was, like I said, he was kind of a reserved guy. So in his memoir, he stated, looking back on the whole thing, I cannot expect that practical astronomers who are already fully occupied with important labors would feel as much confidence in the results of my investigation as I myself did. So he liked his numbers, he was confident about it, didn't really think it was going to get him anywhere. He knew James Chalice at the Northumberland telescope, observatory, and his statement on it was a novel thing, observations and reliance upon merely theoretical deductions. Success appeared doubtful. So, liked the idea, didn't really think to deal with math in it. On October 21st, 1845, Adams takes his data to George Bedell Airy's home and says, hey, I've got this stuff that I found, and to which he's told by the butler, I'm sorry, but he's out. Okay, well, I'll come back to this. So Adams comes back later, and the butler says, I'm sorry, sir, but he's currently dying. Okay, well, can you just leave him this note, right? So, Adams leaves him a note describing what he thinks he's found, and on November 5th, George Bedell Airy actually responded to it, stating, I should be very glad to know whether this assumed perturbation will explain the error of the radius vector of Uranus. This error is now very considerable. So they, again, they knew that there were a lot of problems with this plotted orbit of Uranus, and this was a big thing. The problem here was that Adams got this note and went ahead and, he got the reply to his note, and Adams just set about doing more calculations and trying to improve everything, and Airy never received a response, and just assumed that he had shot down Adams, and he stuffed the note into a filing cabinet. Meanwhile, in France, Dan Leverrier. This gentleman was born in Saint-Lô on March 14th, 1811. It's in Normandy. He studied chemistry at a university, but eventually got into astronomy. This was the Paris Observatory where he spent most of his life. And much like a lot of astronomers at the time, his big interest was what is up with the orbits of these planets? What is up with the, just not even looking for anything, but just what is the general stability of the solar system? This is a big thing that Laplace had spent a lot of time looking into. Now, he was kind of the opposite of Adams. He was an outspoken maybe not boisterous, but he was an outspoken kind of guy. Didn't mince words a lot of the time. In fact, one contemporary said of him, I do not know whether the Soleil is actually the most detestable man in France, but I'm quite certain that he is the most detested. Yeah. Yeah, throw that out. Not well liked. But he was super confident. Yeah, I know, right? Like it's like from the office of the president. But yeah, so he was doing some work on this, and on November 5th, 1845, kind of coincidentally, the same date that Airy sent the note back to, or sent the reply to Adam's note, he published his first paper on Uranus, and then in 1846, in June, he published another paper on it. And as he was finding, he was just coming to the same conclusion that that Adams and a few other people had, was just that there must be another object out there affecting. No other hypothesis remains except that a perturbing body continually acting upon Uranus, changing its motion in a very gentle fashion. So, back to math we go. What did Leverrier did? Or what did Leverrier do? He did math. There we go. Math. Those aren't even, if you know math, those aren't even close to the right equations, but I just put it together. So Leverrier made an initial prediction of the perturbing object, confidently stating that it was within 10 degrees. Okay, so this is where you get his confidence. Such is the capital result at which I have arrived. This perfectly accounts for the observed errors of Uranus. Meanwhile, back in England. On June 26, 1846, Airy gets wind of what Leverrier is up to. And he writes him a letter asking if it accounts for this radius vector problem. Uranus's orbit. 2 days later, Leverrier replies in classic Leverrier fashion, "It is, in fact, one of the considerations which must increase the likelihood of the truth of my results, that they scrupulously account for all aspects of the problem." He continues, "The radius vector is corrected on its own, without having to be considered separately. Excuse me, sir, for insisting on this point." Confident. Now, while this is happening, the British search actually begins. Airy receives this reply from Leverrier and says, okay, he is confident that this solves that problem. Let's go try to find it using Adams' data. So on July 9th, 1846, he writes up a note to James Chalice saying, "I've drawn up the enclosed paper in order to give you a notion of the extent of work incidental to a sweep for the possible planet." Basically, go hunt for the damn thing. But he gave him some details based on what Adams' work had looked like. The thing was that he gave him a region of sky 30 by 10 degrees to sweep. Not a small piece of sky. Reference, like, the moon is about a half a degree, right? The object he's looking for is a couple of arc seconds, right? And it was estimated that the entire process would take about 300 hours of observing, which, not great in England. Like, cloud cover there is not super reliable. So the process that they undertook was that they went through 80 separate, the process was to go through 80 separate sweeps, taking an hour each. As each star crosses the telescope's hair, that position is called out by an observer and recorded along with the time. Okay? This is the equivalent. Now you can just do this with a camera, right? Back then, you had to have people calling out numbers and calling out objects and calling out, recording everything down. Right? And then you would map the field and go back to compare. Remember, we're looking for a change here. We're looking for something to differ. Right? The stars shouldn't move. The planet should. So we're trying to figure out what is missing here. So, and what's kind of interesting here is that Airy had a wealth of amateur astronomers at his disposal, and he opted not to use them for reasons unknown. There's some suspicion that he kind of wanted this whole thing to be a very British discovery. They kind of held somewhat of the crown at the time in astronomy, which is more worldwide. And yeah, he could have reached out, he could have gone to other observatories with Adams' results, never did. Just for whatever reason, just did not go beyond Chalice and his telescope. Chalice reported back to Ares saying, I get over the ground very slowly, and I find that to scrutinize thoroughly in this way, the preferred portion of the heavens will require many more observations than I can take this year. So this is going to go on for a while. August 31st, back in France. Leverrier, he determines that with further calculations that he figured that the planet should be about, this planet should be about 3 arcseconds across. It's also worth noting at this point that Leverrier's calculations took about 10,000 pages of data by this point. So not only, he stated not only should it be possible to see the new planet in good telescopes, but also to distinguish it by the size of its disk. So hoping that, similar to how Uranus was discovered, Neptune would be obvious as well. Back in England. Adams writes to Airy with his newly refined predictions, but Airy's away on holidays. Actually, Adams had also tried to present his results at the, there was an astronomical society meeting, and a conference, and he had intended to present his results, but he showed up on the wrong day, so they didn't get it. France. Leverrier writes to Johann Gall, who is an assistant to the Berlin Observatory, which is kind of sneaky, right? Because he didn't write to the head of the observatory, he wrote to the assistant. Why? Because the head of the observatory is the manager, and he's going to look at this and say, why are you wasting my money on this? The assistant is going to look at this and say, I could discover a planet? Great, right? He writes, I'd like to find a persistent observer who would be willing to devote some time to an examination of a part of the sky in which there may be a planet to discover. If you got that, I think you'd be pretty excited. So, Johann Gall and one of his students, Henrik de RASC, set out to try to find the planet. They got permission from Henk, who was actually the head of the this astronomer Johann Henk, who was actually the head of the observatory at the time. And on September 23rd, 1846, they couldn't find anything in that area that looked like a disk. Just nothing jumped out at them. So what they did was, and this was actually Henrik de RASC's idea, he took the, he had the idea to say, well, hey, we just got this new star atlas, let's start doing a comparison, let's go back and forth, right? See if there's an object that we can see that doesn't line up with the star chart. This is the telescope that they were using, quite a long refractor. And they started, so they began the hunt in that manner. And at one point in the night, Henrik de RASC exclaims, that star is not on the map. They found it. The following night, they go out again, and sure enough, it's moved a little, right? They had found Neptune. So this was all based on mathematical predictions, based on data that have been observed with Uranus. Quite amazing. Johann Henk, who was the Berlin Observatory director at the time, he had permitted the search, and then he had actually, they called him up and said, hey, we think we found it, kind of thing, right? And he said that the disk is only seen when it is known to exist. I think people in here might have been through that experience before. So you can't actually see a disk, but if you don't know it's there, you probably won't notice it. And there was quite a lot of, obviously, this is a big deal, right? We've just found a new planet. Leverrier Johann Gall writes back to Leverrier as fast as he can. It tells him that the planet actually exists. And the news spreads across Europe. This is now the biggest thing that has happened since the discovery of Uranus. Henk writes that he'll be forever linked with the most striking proof imaginable of the validity of the law of universal gravitation. John Hind, a British astronomer, writes this discovery may be justly considered one of the greatest triumphs of theoretical astronomy. Henry Schumacher writes, this is the noblest triumph of theory that I know. These were all big names of the time. Variety writes, amazing. 5 stars. Rave reviews. Back in England. So now it's October 12th. So here's the thing to keep in mind. Britain had a shot. They really had a shot at this. And they missed it. Right? Not only did they miss it, Chalice actually had seen Neptune. Quote, I have been greatly mortified to find that my observations would have shown me the planet in the early part of August if I had only examined them. Right? So now things get a little bit tense. Chalice says the planet, however, was secured, and 2 positions of it recorded 6 weeks earlier here than in any other observatory, and in a systemic search expressly undertaken for that purpose. What he's saying here is Britain found it first. Okay? So, despite the fact that Leverrier and his German observatory had found the planet, Britain was trying to go back and say, we're used to rewriting history, and actually I think we found it first, right? Based on the fact that they had done the hunt and Adam's data had come up. I mean, the translation of this at this point is, right? But of course, he tells everyone this, right? He's writing these letters, to various publications, stating this, and Airy's getting, George Bedell Airy, the Royal Astronomer, he's getting involved in this, and the general response was, who the heck is this Adams guy? We haven't seen any of his data. Remember that Leverrier was publishing this data all the time. He was saying, look, I have this. He was going to observatories all over the place saying, please, for the love of whatever, just try to find my planet, right? He didn't, he was boisterous and outspoken, and that got him results. I'm not recommending that to the kids, but, it's a method, right? So, meanwhile in France, they have some reactions to this. Francois Arago, who was the head of the Paris Observatory, said, Leverrier is called upon today to share the glory so loyally, so rightly earned, what's the word loyally in there, with a young man who has communicated nothing to the public and whose calculations more or less incomplete are totally unknown in the observatories of Europe. The French papers get on it. So this is meant to be Adams. And here's looking. So Adam, if you'll notice, I'll just spell out the whole satirical comic here, because it's new comedy. Explaining jokes. So he's looking at the data, right? And he can't see the data that Leverrier has generated, and Leverrier is finding the planet. Notice the flags. Okay, there's a little bit of British versus France thing going on here. This one spells that out quite a bit. Really obvious. Look over here. Sorry, blinded by national pride. So the French, the French public was really got into this. They looked at this as these claims by Britain were just total farce. So on November 5th, 1846, there was a meeting of the Royal Astronomical Society, and this was to come together and say what happened, right? How did this whole thing get missed? What's interesting about it is that George Bedell Airy and Chalice were kind of meant to look the fool, they were not well regarded as in this. But Adams actually was given an opportunity to present his data, and people came away with it saying that you did excellent work here, and you kind of drew the short straw on this. It's a bit lengthy, but it encapsulates the general sentiment of the British astronomers at the time. It appears from the delivery of Mr. Airy's address that he is somewhat to blame for the loss of the complete realization of the discovery of the new planet by Adams of Cambridge, and there appears to have been an attempt to make a Cambridge snuggery affair of it. I love that one. For Chalice and the Northumberland Equatorial, talking about the telescope that they were using. But the big thing here to point out is that he did call out Adams, right? 1847 in France. The astronomers there catch wind of Adams' work, and they kind of start to change their tune. Time had passed, things had settled a little bit, And a French astronomer said, I only see a talented young man who has been served badly by circumstances in this one time, in whom one must applaud in spite of it. I say to him, the laurel which you merited first, another merited also, and has carried it away before you had the boldness to seize it. So, time to recap. What I find kind of crazy about this is just how fast things were moving at the time for the 1800s. Right? This is nowhere near the information age, right? Yet at the time, both these mathematicians were taking data that were published by astronomers at the time and trying to work this problem independently. Right? They kind of knew of it. Like Adams knew a little bit of Leverrier, but not a heck of a lot. And it's incredible. These two mathematicians were independently working on this problem at the same time, without, really, spending any time under a telescope either. So, yeah. So how close were they? Adams was, at best, was within 2 degrees. Leverrier, less than a degree. So pretty good. This chart here shows a number of predictions by Adams. He refined his data a lot, and it did bounce around a little bit. So there's some contention as to whether he would have really actually been able to find it, but he did get reasonably close a couple times. But this is Leverrier's prediction. So in general, Leverrier's prediction, pretty good. Right? And actually, much of the error that they saw was due to their reliance on Bode's law. So when they were doing these, if you remember Bode's law from way back when they were doing this math, they had to rely on just kind of a guess as to how far away the planet was from the sun. And so they just used Bode's law because it was kind of working. They didn't really want to admit to that, but that's what they were using. Here's a bit of a problem with this. So the predicted distance was 38.8. The actual distance to Neptune, 30.11. Right? So if it had actually followed Bode's law, they would have been able to find it a lot faster. So what's kind of cool about this story, though, is that Adams and Leverrier actually did end up meeting in 1847, and they ended up chatting like old friends. They were like in their eyes, they were never rivals. This whole Britain versus France thing was just a bunch of BS, right? And they were just two mathematicians setting out to solve a problem at the same time. So, what's next? Planet 9, of course. Now Pluto. This is pretty recent. I've been doing a lot of old stuff. Here's something new. All right. 2016, January, Konstantin Batygin and Michael E. Brown published a paper on the possibility of entitled Evidence for a Distant Giant Planet in the Solar System. All right. So where did this come from? Kind of a very similar place. So we've been finding out, so this is the solar system, right? So we've got all the inner planets, and then the outer planets, like the inner planets are in there, and these are the outer planets, right? These are Kuiper belt objects. Do you notice something? Kind of off to one side, right? I'm glossing over a lot of math here and orbital mechanics, but I mean it's like 5 to 10, so I don't have time to get into it. But this is what they are proposing. That there is the possibility that, and they're actually really confident about this, like Leverrier levels are confident about this. And they're predicting that there is a large planet out there. There was actually some news last week talking about how, just due to the fact that so many other solar systems that we've seen actually have planets of this variety, that it would make sense for our solar system to probably have one as well. So there's some really good evidence for this, and they're still hunting for it. So at some point, somebody might find it. I'd like to acknowledge this book, the Neptune File. It was actually the source for a lot of the stuff that I put into this presentation. I don't know how hard it is to find. I know that I can't find, like I've not been able to find a digital copy of it, unfortunately, which would have been kind of nice. But if you are, like if this interests you at all, there's a lot more to this story. There was a whole controversy about how the planet was to be named, etc. That's all here. I really recommend it. If you can find it. If you can't find it, or you just don't want to pay for a book, or you just want just an easy option, I'm happy to loan this out, providing I get it back at some point. But I'm very happy to loan this out to anyone who wants to give it a read. And that's it. Thank you very much. So now that you're all nice and sleepy, we're going to head to Boston Pizza. Well, were there any questions? I could possibly chime in on some things if you had questions. Yeah.
Neptune's orbit closer to the sun than they imagined. What would the reason for that be? Sorry.
Yeah, I don't know. Yeah, I don't know if there's any real reason for it. I think most people at this point just suspect Bode's law to be a happy coincidence. Kind of one of those things where, like in nature, you find all sorts of sequences everywhere, right? And they just match to it both because math and nature tend to get along, kind of thing, right? So I think at that point, like if there is some sort of effect, I think the further away that you get from the sun, there is the possibility that it just has less of an effect. But it's interesting that it is a little bit closer, right? All right, let's look at Boston Pizza.